SwayamPrabha. Digital India. Educated India.
Welcome everyone to lecture 7. So, today we are going to learn a new concept, that is of the principal stress components and principal planes. Okay. Alright, so what do we really mean by this? So, remember, at any point in the body we have different tractions on different planes, right. So, we have to find a plane on which the normal component of traction becomes maximum or minimum. So, at a point there are several planes, each of the planes will have different normal component of traction, and then we find those planes on which that normal component of traction is getting maximized or minimized. Okay. So, those planes are principal planes, and the value of the normal traction on those planes, they are called principal stress components. Why it is important? It is again, there is a fracture theory which says that a body is going to fail at a point if the principal stress component reaches a threshold limit. Okay. So, therefore, at any point we should know what is the principal stress component, so that we can know whether the body is within the limit of fracture or not, right. Whenever you design the body, we have to make sure that the body does not fail. Okay. So, let us see how we can find out principal stress components or principal plane. So, we have this body and we are at a point x. So, let us say the stress is sigma. So, that means the traction on a plane with normal n is sigma times n, and what is going to be the normal component of traction. So, this means sigma n n, if I write, which is T n dotted with n, it is simply sigma n dot with n, right. So, that is the normal component of traction on any plane, and I have to maximize this or minimize this. So, how to maximize or minimize? So, if you have a mathematical formula, you want to maximize or minimize, you set the derivative with respect to the unknown equal to 0, that gives you the equation. Solve that equation and you get the corresponding values. Okay. So, that is what we have to do here. So, let us choose a coordinate system, all right. So, sigma n n is then the stress matrix which is sigma 1 1, 1 2, 1 3, 2 1 and likewise, and then it gets multiplied with the normal vector, which will have 3 components n 1, n 2, n 3. So, when you multiply these two, you get a vector, and then you dot it with the normal n 1, n 2, n 3. Okay. So, can we write this down in terms of summation? So, yes, as you can remember from the first lecture, when you do matrix vector multiplication, so this whole thing is then there are two summations, summation over I and summation over j sigma I j n j into n I, right. This whole thing you could write in the summation convention. So, we have the unknown is n 1, n 2, n 3. So, we have to find out the plane on which sigma n n is getting maximum or minimum. So, n 1, n 2, n 3 are the unknowns and stress matrix will be given to you. Okay. So, I will write here. So, stress matrix is known whereas the normal direction. So, normal direction is the unknown. And you see, like any direction, this has to be of magnitude 1, right. So, n 1 square plus n 2 square plus n 3 square has to be equal to 1. So, not all the 3 components are independent of each other. So, n 3 is the square root of 1 minus n 1 square minus n 2 square. So, in this formula you could replace n 3 with this square root, but then the function becomes very complicated. You have square root and then you have to differentiate with respect to n 1 and n 2, right. So, there is another way to do this is by using Lagrange multiplier. So, the function that we have to minimize, this function, I add to it the constraint term, where constraint is that the magnitude of the normal vector is unity. Okay. So, the function to be minimized, so let us call it by f, which is a function of the 3 components n 1, n 2, n 3 and a Lagrange multiplier lambda, and that function is summation over I j sigma I j n j n I minus lambda times summation over I j whatever you want n I minus 1. Okay. So, that is the function to be minimized. So, the second term here lambda times, so summation over n I that is the magnitude of the normal vector, which has to be equal to 1, right. And this minus sign in front of lambda, you could also have it positive, it does not matter. Okay. So, this is the function which we have to minimize or maximize. So, we take the derivative with respect to each of the components, right. So, let us for example, take the derivative with respect to n 1. So, del f by del n 1. So, sigma I j, remember it is a constant, it does not depend on n. So, we have summation over I j sigma I j and then del n j by del n 1, okay, del n j by del n 1 times n I plus again the same term, because we have to apply product rule here, sigma I j n j times del n I over del n 1, okay, minus lambda times, we have the summation term, and it is n I into n I, same thing appearing twice. So, you take the derivative, you get a 2. So, it is 2 times del n I over del n 1. Okay. So, that is what you have, and you have to set it to 0. Let us try to see what is this really. So, what will be del n j by del n 1? So, that is going to be 1 if j is equal to 1, otherwise it is 0. So, we are going to assume n 1 does not depend on n 2, n 2 does not depend on n 3, n 3 does not depend on n 1. So, del n 1 by del n 1 is 1, but del n 2 by del n 1, that is equal to 0. Okay. So, I could write here this small identity that del n I over del n j. So, if I and j are same, it is 1, if they are not the same, it is 0. So, there is a very nice term in mathematics for this, that is called delta I j, Kronecker delta function. Okay. It is another thing that you can remember, add to your vocabulary, Kronecker delta function. So, this function is 1 if I and j are same, otherwise it is 0. So, I should write that here. So, we can use that in this derivative. In fact, why do not we generalize this? Instead of n 1, can we think of taking derivative with respect to, let us say, n k, where k could be 1, 2, 3, anything, right. So, del f by del n k is then summation over I j sigma I j del n j by del n k, which is simply delta j k n I plus summation over I j sigma I j n j delta I k minus 2 lambda summation delta I k, okay, and that is equal to 0. Now, we can further simplify this. Look in the first term, for example. In the first term, we have delta j k times sigma I j. So, there is a summation over j, right, and we know that delta j k is 1 only if j is equal to k. So, when you do the summation over j, j equal to 1, 2, 3, then we know that only one of the terms from that summation is actually going to survive, which is when j is equal to k. The other terms in the summation will simply become 0. So, that means you can get rid of this summation over j, and wherever you have j, replace that with k, isn't it? So, this is then a single summation over I sigma I k n I. See what happened? The summation over j is gone, and the second index of sigma has been replaced with k, right, because only j equal to k is surviving. Likewise, the second term, what does that become? So, this is now summation over j sigma k j n j. So, here the summation over I is eliminated and I is replaced with j. Okay. Minus, so the last term it is simply minus 2 lambda and okay, so I guess I have missed something here. So, in the last term here there should have been one n I also, right. So, one n I is also going to be there. So, likewise here you have one n I also. So, finally, the summation over I is then gone and I is replaced with k. So, this becomes 2 lambda n k and that is equal to 0. Okay. Now, I am going to say that the first and second term here they are actually the same. Can you guess why? See, the first term is sigma I k n I and the second term it is sigma k j n j. So, there is summation over j in the second term. Now, that j could be anything, right. It is a summation variable. Why don't we replace that j with I? It is a dummy variable, you could replace that with a, b, c, d, anything you want. So, if I replace that with I, then we have summation over I sigma I k plus sigma k I times n I minus 2 lambda n k equal to 0. Okay. What more can we say now? You see, you have already derived that the stress matrix is symmetric. So, sigma I k is same as sigma k I. So, the thing inside the bracket we can then write it as 2 times sigma k I, right, and then 2 cancels from both the terms and we simply have summation over I sigma k I n I minus lambda n k equal to 0. Okay. So, this is one equation that you have derived. See the usefulness of the summation. Otherwise, you would have to expand the whole thing and then work it out. It is such a big mess. With the summation, it is a small thing, right. And also, you could take the derivative with respect to n k instead of doing it by n 1, n 2, n 3 separately. You have done the whole thing with a single derivative n k. So, these are the derivatives with respect to n 1, n 2, n 3, and what happens when you take the derivative with respect to lambda? Look at this function. So, if you take the derivative with respect to lambda, what do you get? Del f by del lambda equal to 0, that simply gives you that constraint, that summation over I n I is equal to 1. So, I am going to write here. So, del f by del lambda then gives you summation over I n I minus 1 equal to 0. Okay. So, you have basically 4 equations now, right. So, this holds for k equal to 1, 2, 3. So, there are 3 equations here and one more, total 4 equations for the 4 unknowns. So, 4 equations for 4 unknowns. Now, we are going to relook at those 3 equations to see what this really is. What is the first term? See, it is sigma k I n I. So, it is basically the matrix sigma multiplied with the vector n, right. For k equal to 1, you look at the first row of sigma and multiply with the vector n. For k equal to 2, second row of sigma multiply with the vector n. K equal to 3, third row of sigma multiply with the vector n, right. So, if you can write all the 3 equations together, you actually get a matrix equation, which looks like the following: sigma matrix into the vector n is equal to lambda times the vector n, is not it? So, the 3 equations are actually in this condensed form. And can you recognize what is this equation? So, for a matrix A x equal to lambda x, what is that equation? So, that is the eigenvalue eigenvector problem, right. So, it is now a eigenvalue eigenvector problem. Right. So, what this tells us is that the direction n is the eigenvector and lambda is the eigenvalue, right. So, I am going to write here. So, n is the eigenvector of sigma and lambda is the eigenvalue. Furthermore, if n is an eigenvector, then any scalar multiple of n is also an eigenvector. Can you recall it from your maths class? So, if you have A times x equal to lambda x, then A times B x is equal to lambda times B x. So, both x as well as B x are the eigenvectors with the same eigenvalue lambda. So, we have the flexibility over the eigenvector, right. The magnitude of eigenvector could be anything, could be arbitrary as far as this equation is concerned. But then the fourth equation tells us that the magnitude has to be 1. So, that sets the solution basically. So, we have to choose the eigenvector of sigma, but unit node or unit magnitude. Okay, because we have to also satisfy the fourth equation. So, the whole problem about finding the maxima or minima of the normal component of traction has reduced to this eigenvalue eigenvector problem, right. Also try to notice one thing, what is the left hand of this equation, sigma times n, what is that? Isn't that the definition of traction? Traction on the nth plane is sigma times n, right. So, T n, we know that this is sigma times n, which from our equation is equal to lambda times n, isn't it? So, what do you infer from here? So, what we infer is n is the eigenvector of this equation, but now from this box the traction is along the eigenvector, is not it? So, remember n was the direction of the plane to begin with, which now turns out to be the eigenvector, and now we see that the traction has to be along that direction. The tractions on principal planes have only normal component, they have no shear component. This is what it says. So, this means the traction on principal planes have no shear component, because you can see it is along the normal. And so, what is the magnitude of the traction? It is simply lambda, right, because n is of unit magnitude. So, the magnitude of traction is simply lambda. Well, you have to put a bar here, because lambda could be plus or minus. Okay, so, what is the final message? That the principal planes are the eigenvectors of sigma. Okay, basically I should say normal to principal planes. And the principal stress components they are the eigenvalues of sigma, right, lambda itself. So, that is really a nice result finally, simple and nice result. So, at any point you have the stress matrix and you want to find out the principal direction and principal stress component, simply find out the eigenvalue and eigenvector of the stress matrix, right. Now, the other question is, how many principal planes are present? Because you see, by definition principal planes are the planes on which the normal component is getting maximum or minimum. So, how many such planes can be present? So, here again you will see the advantage of stress matrix being symmetric. First of all, this stress matrix, it is a 3 by 3 matrix, right. So, how many eigenvectors can be there? So, a 3 by 3 matrix will have maximum 3 eigenvectors if the eigenvalues are all different. And because the stress matrix is symmetric, it ensures that it has all those 3 eigenvectors. And what can we say about the directions of the 3 eigenvectors? So, it turns out symmetric matrices, the eigenvectors are perpendicular to each other. So, can we prove it? Yes, we can prove it. It is quite simple. Let me show that to you, that for symmetric matrices, eigenvectors corresponding to different eigenvalues are perpendicular. Okay, there is a very small and simple proof. So, suppose that n1 is the one eigenvector and n2 is the second eigenvector. So, sigma times n1 is then lambda 1 into n1, right, and the other one is sigma times n2 is equal to lambda 2 times n2, where lambda 1 and lambda 2 are different. So, let us dot the first equation with n2, okay, and the second one with n1. So, what does the first equation now give me? So, I have sigma n1 dot with n2 equal to lambda 1 of n1 dot n2, dot product of the two eigenvectors, whereas the second equation gives me sigma n2 dot with n1 is equal to lambda 2 of n2 dot n1. Okay. And now, you know from the matrix vector operation from your first lecture that this is also equal to, you can bring this sigma on the other side and it becomes transpose, sigma transpose n1 dot with n2, but we know that sigma is symmetric. So, transpose of sigma is same as sigma. So, this is basically same as sigma n1 dot with n2, and that has to be equal to lambda 2 n2 dot n1. Now, compare these two equations. If we subtract these two, what do we get? The left hand side of these two equations are the same, right. See, it again happened because your stress was symmetric. And what do you get on the right hand side? So, this means lambda 1 minus lambda 2 into n1 dot n2 is equal to 0. That means n1 dot n2 is 0 because lambda 1 and lambda 2 are different. So, this further implies that n1 and n2 are perpendicular. Okay, so, that is a very nice derivation, simple. So, for a symmetric matrix, if it has 3 different eigenvalues, then the corresponding eigenvectors will be perpendicular to each other. So, we have derived that the eigenvectors are perpendicular. So, since the eigenvectors are always perpendicular, we can choose them as the basis of our coordinate system. So, now how does the stress matrix look like in the coordinate system of eigenvectors. So, what you have to do now? Whenever you want to find the stress matrix in a coordinate system, you find the tractions on the basis vectors of the coordinate system, and in this case the basis vectors are the eigenvectors. So, the traction will be simply lambda times n, right, and it is along the normal. So, traction has no shear component, it has only normal component. So, the matrix is then simply a diagonal matrix having lambda 1, lambda 2, lambda 3, and the off diagonal components all becoming 0, because the off diagonal components denote the shear, and we know that on these planes we have no shear component of traction. So, this is also again very nice, that given any arbitrary stress matrix, we can always diagonalize the stress matrix by choosing the coordinate system which is aligned along the eigenvectors of the stress matrix, is not it? And you know, physically this is a very nice picture also. Think of the cuboid. So, we had that cuboid and in the general case, on the faces of this cuboid you have both normal and shear component of traction, right. So, this cuboid has its faces along E1, E2 and E3. But now, if we choose the cuboid such that its faces are along the eigenvectors. Okay. So, let us think of the cuboid with faces along the eigenvectors. So, maybe something like this. And now the perpendiculars are the eigenvectors n1, then you have n2 and you also have n3. And for such a cuboid, the faces will have no shear component, right, because these planes are principal planes having no shear component. So, on these faces you only have the normal components which are lambda 1, lambda 2 and lambda 3. So, the planes of this cuboid have no tendency to shear, they can either get pulled apart or they get pushed into. If any of the lambdas is negative, that means the corresponding plane is getting compressed, it is getting pushed. If the lambda is positive, then the corresponding planes are getting pulled, getting in tension, right. All right. So, with this I will end the lecture, and in the next class we are going to see, just like we maximized or minimized the normal component of traction, we can also think of maximizing or minimizing the shear component of traction, right. At a given point we have so many planes, on what plane the shear component of traction is getting maximized. And again, why do we care about it? It is again, there is a fracture theory, there are many kinds of fracture theory. One fracture theory or failure theory says that the body fails if the shear component of traction reaches a critical value. So, if you want to analyze the body according to that theory, then you need to know on which plane the shear is maximum, right. So, we will see that in the next class. Okay. Thank you.